This video is going to cover section 6.2, which is titled Properties of Power Series, and we're going to be focusing in on two specific properties that we have for power series, and that is the ability to integrate and differentiate a power series. And sometimes this is something that we need to do in order to be able to represent a function as a power series. And so in theorem 6.4, it shows how this is done. So if we have a specific power series that is shown here, then when we take its derivative, we just use the power rule. So notice we have x minus a to the n, and using the power rule, you take the power to the front and you subtract 1 from the power, and that's what you see here. So if we take that power to the front, it's going to be n times c sub n. And then notice the new power is subtracted 1 right here. And so that affects what the individual terms in the sum look like. And then the same thing applies when we take the integral. So when we take the integral, we add 1 to the power, and then we divide by that new power. And then notice there's also a constant of integration. So you got to make sure, even when we're integrating a power series, you have to make sure that you're including that constant of integration, which should make sense. Now, going back up to the original series we had, notice that our radius of convergence is r. So r radius of convergence. Now, notice here when we take the derivative, r is still the radius of convergence, and when we take the integral, when we take the derivative and the integral, r is still the radius of convergence for both of those. So let's make a note of that. R is still the radius of convergence. And the reason why that's significant is it doesn't make, so let's say r is 2 to begin with. Well, just because you differentiate it doesn't make it 4 or 5 or some other value. It stays fixed, whether you integrate or differentiate. And then one other thing to just remember, last section we learned how we could use the geometric series to represent a function that has the form 1 over 1 minus x as a power series. And we're going to use that to our advantage here. So in this first video, we're going to look at how we can use differentiating or taking the derivative of a power series to help us find a power series representation. So example 1, we want to determine the power series representation for the function g of x equals 1 over 1 minus x squared. And in comparing that, if we compare with our power series representation for a geometric series, remember it needs to look like 1 over 1 minus x, and it's not the same. However, if we were to integrate g of x, we would get this 1 over 1 minus x. How does that look? Let's go ahead and take a look here. So we will say first, if we were to integrate g of x, that's going to look like the integral of 1 over 1 minus x squared, right? 1 over 1 minus x squared dx. And how would we go ahead and integrate that? What integration method would we use there? Hopefully you're saying we would use the U-Substitution method, because if u is equal to 1 minus x, then we know that du would be equal to negative 1 dx. And so when we rewrite this, this is going to be the integral, because that negative dx, we're going to have a negative out front, and then we have 1 over u squared du. And when we go ahead and use the power rule, that's going to, remember that's u to the negative 2, so we add 1 to that, we get u to the negative 1, divide by negative 1. This is basically going to become 1 over u plus c. And then we back substitute, because u was equal to 1 minus x. This is 1 over 1 minus x plus c. So voila, you take the integral, we get to that form that we're used to. This is our power series, geometric power series form. And so we can plainly state that the integral of g of x d to dx is equal to 1 over 1 minus x plus c. Actually, let's write the c first. You'll see why here in a second. So let's write c plus 1 over 1 minus x. Okay, so let's go ahead now and rewrite this as a power series. So we have the integral of gx dx is equal to, and the reason why I wrote the c at the front here is because I don't want that to interfere with this power series representation, because we know this is the sum of x to the n, right? And term by term, so we have the constant at the front, and we know if we then write out the first 4 or 5 terms of this series, we're going to end up with x to the 0, which is 1, plus x to the first, plus x to the second, plus x to the third, and so on. So that's what our power series looks like. Now, we don't want a power series representation of the integral of g of x, right? So what we just wrote was a power series representation for the integral of g of x. We want a power series representation for g of x. So if we want g of x, how do we get rid of this integral? Well, knowing what we know about calculus, we just take the derivative, right? So if we were to take the derivative of the integral of g of x, that gives us just g of x. And so that's why we need to know how to be able to take the derivative of a power series. So first, the derivative of a constant, c, is 0, plus we have then the rule that we just learned in the theorem on the previous page. Notice when you take the derivative, one thing I did not point out before, notice that our index term, we lose a term. So we started with n equals 0, and then when you take the derivative, it goes to n equals 1. And that's because our first term, c0, is going to be a constant. And so it's just going to go away. It's going to become 0. And so this is going to change to n equals 1. And then remember, we're using the power rule. So this is going to become n, bring the power down, and then subtract 1 from the power. And so term by term, what does this look like? Well, again, the derivative of c is 0, plus the derivative of 1 is 0, plus the derivative of x is 1, plus the derivative of x squared is 2x, plus the derivative of x cubed is 3x squared, and so on. And one thing we did not talk about through all this was our power series representation. So remember, we're using the geometric power series here. So this is true. This geometric power series happens. This is equal to this for absolute value of x is less than 1, which means our radius of convergence here is 1, which means even after we take the derivative, remember the radius of convergence does not change, so r is still 1. And so we have our representation. Let's go ahead and rewrite this just so everything looks nice and clean. Let's say, so our g of x is equal to sum from n equals 1 to infinity of n times x to the n minus 1. And then we can write our interval of convergence as 1. Okay, so that's how we can use taking the derivative to find a power series for a function. Let's go ahead and end this video, and then we'll have one more video which we'll talk about integrating power series. That'll be example 2. Thank you.